In this tutorial, I present my first AI-based sea ice lead classification algorithm, developed using the Week 2 material. The aim is to demonstrate how satellite imagery and IRIS-labeled data can be used to train a supervised machine learning model to distinguish between sea ice and leads. The problem addressed here is a supervised binary classification task, where the goal is to distinguish between sea ice and leads. On the left is a region of interest extracted from OLCI satellite imagery, and on the right is the corresponding iris-derived label mask. In this mask, lead pixels are labeled as 1, and ice pixels as 0. These labels provide the ground truth required for supervised learning, allowing the model to learn the spectral and spatial characteristics that distinguish leads from surrounding sea ice. Next, the labeled region of interest is converted into a patch-based dataset. Instead of classifying individual pixels, I extract a 3x3 pixel neighborhood around each pixel location across all 21 spectral bands. This means that each input sample has shape 3x3 by 21, which allows the model to learn spatial context and fracture geometry, rather than relying only on spectral information. The corresponding label mask is flattened so that each patch has a single ground truth class, producing a supervised training dataset. For the classification model, I use a convolutional neural network. A CNN is appropriate for this task because the input data consist of small image patches, where the spatial arrangement of pixels is important for identifying lead features. The convolutional layers allow the model to learn local spatial patterns, such as edges and linear structures, which are characteristic of sea ice leads. Once trained, the CNN outputs a probability for each patch, which is then converted into a binary prediction, distinguishing between ice and leads. To evaluate the performance of the CNN, I apply it to a held-out test dataset and summarize the results using a confusion matrix and standard classification metrics. The confusion matrix shows that sea ice is classified very reliably. Out of 990 ice samples, 963 are correctly identified, giving an ice recall of approximately 97%. Lead detection is more challenging. The model correctly identifies 762 lead samples, but misses 228 leads by predicting ice instead. This corresponds to a lead recall of around 77%. However, lead precision is very high, at approximately 97%, meaning that when the model predicts a lead, it is usually correct. This indicates a conservative classification behavior that prioritizes avoiding false lead detections. Finally, I apply the trained CNN to the entire region of interest to generate a spatial prediction, so we can visualize the result as a lead mask. The code first builds a patch dataset for every valid pixel location in the ROI, and then runs model.predict to output a probability for each patch. I convert those probabilities into binary class labels using a threshold of 0.5, where 1 represents lead and 0 represents ice. Those predictions are then reshaped back into the original image geometry to form a two-dimensional mask. In the output, the model captures connected, linear fracture features consistent with lead networks, although there are some small speckle detections and some thin leads may be missed, which matches the precision recall trade-off seen in evaluation. To summarize, this tutorial followed the full Week 2 workflow. First, iris-labeled satellite data are loaded and converted into a supervised dataset. The labeled region of interest is then transformed into a patch-based representation, where each sample contains spatial and spectral information. A convolutional neural network is used to classify these patches into ice and lead, and model performance is evaluated using a confusion matrix. Finally, the trained model is applied spatially to reconstruct a predicted lead mask for the entire region of interest.